Australia isn't just a land of beaches and bush. It's a continent carved by time, fire, water and rock. From glowing red monoliths and bubblegum pink lakes, to lava tubes, sea cliffs and ancient reefs. This island continent is home to some of the most strangest and most spectacular geological features on Earth. In this video, we're counting down 18 of the most mind-blowing natural wonders that reveal the hidden forces shaping Australia over billions of years. Some of these places look like alien worlds. Others are so massive, mysterious or remote that even locals haven't heard of them. Whether born from volcanoes, carved by erosion, or left behind by vanished seas, each one tells a story written in stone, and some of them will absolutely surprise you. The Bungle Range in Western Australia. In the remote Kimberley region, the Bungle Range rises like a lost city of striped beehive domes, their banded flanks glowing orange and black in the shifting sunlight. These strange rounded towers, some up to 250 metres tall, are built of ancient sandstone, a remnant of sediments deposited in a shallow sea during the Devonian period over 350 million years ago. Grains of sand once settled here when life on land was sparse and early fishes swam in tropical waters. Over eons, those sands were buried, compressed, and cemented into hard quartz sandstone, the bedrock of Purnululu National Park's iconic range. The sculpting of the beehive domes began long after the sandstone formed. As the land slowly uplifted, rain and rivers started carving into the layered rock. Erosion and weathering worked patiently, exploiting slight differences in hardness between layers. Softer beds of sandstone wore down into gullies while tougher layers persisted as rounded crests. Wind carried fine grit that sandblasted the rock, and seasonal torrents of water gouged channels, isolating the hardest portions as freestanding domes. Over millions of wet summers and dry winters, this differential erosion chiseled out the landscape's peculiar geometry, an army of domes clustered and stacked like giant termite mounds. What makes the Bungles truly enchanting is the striped coat each dome wears. Dark grey-black bands alternate with bright orange across the curved surfaces. The dark bands are living rock skins, thin biological crusts of cyanobacteria that thrive on moisture, binding the surface and staining it with their pigment. In the dry season, the cyanobacteria lie dormant, but their presence slows erosion in those bands and creates the darker tone. The orange bands, by contrast, mark bare sandstone where iron minerals have oxidized in the sun and where the rock dries out too quickly for the bacteria to take hold. Together they form an otherworldly tiger stripe pattern, nature's artwork born from biology, chemistry and weather. In this hidden corner of Western Australia, walking among the Bungles feels like stepping into deep time. The air is thick with the scent of spinifex grass and sun-baked rock. Beneath your boots lies the Devonian seafloor, now raised high and transformed into a maze of orange domes. Wave Rock in Western Australia. On a vast wheat-belt plain of Western Australia stands an impossible sight, a 15-metre high wave of stone about to break eternally over the scrub. This is Wave Rock, a natural rock formation that perfectly mimics an ocean swell mid-crest. Its broad flank arcs and curls, streaked with mineral colours like spray frozen in mid-flight. Though it lies far from any sea, Wave Rock was shaped by its own ocean, an ocean of groundwater and time, which together sculpted this granite monument. Wave Rock is part of Heiden Rock, a solitary hill or inselberg of very ancient granite rising above the plain. An inselberg is an isolated hill, knob or mountain that rises abruptly from a gently sloping or virtually level surrounding plain. The term, from the German meaning island mountain, refers to landforms that resist erosion while the softer surrounding rock is worn away, leaving the more durable rock standing alone in the landscape. The granite here is Monzo granite, formed around 2.63 billion years ago, a piece of the Yilgarn Craton that makes up Earth's old Archean core of Australia. Its mineral grains of feldspar, quartz and biotite cooled slowly deep underground eons before multicellular life existed. Much later, between 100 and 130 million years ago in the Cretaceous, this region was uplifted and the granite batholith began to fracture and weather beneath the surface. Chemical weathering by groundwater etched away at the rock along joints, hollowing out concave slopes under the earth. In the warm and wet climate of that age, water filtered through soil and reacted with the granite's minerals, transforming feldspar to clay and weakening the rock at the base of the hill. These processes created an underground scalloped shape, the embryo of the wave, while the upper rock remained solid. As Australia drifted northward and the climate dried, erosion stripped away the softer weathered rocks. Over tens of millions of years, the land surface lowered, exposing the buried bedrock domes of Haydn Rock, like a giant releasing carved sculptures from stone. What we see now is a classic flared slope, as geologists call it, a steep concave base of an inselberg that was formed by concentrated groundwater attack near the soil line. The curvature continued to refine as the newly exposed rock face was further scoured by rainwash. Water running down the slope kept dissolving and carrying off loosened grains, amplifying the hollow and undercutting the base so that the wall above overhangs like a cresting breaker. Today, wave rock stands arrestingly lifelike. Its surface bears streaks of orange, yellow and grey, the rainwater's canvas, where runoff has encouraged lichens and minerals to stain the granite face. Up close, you can trace the ripples and undulations on the stone, each a subtle record of how water once pooled or flowed, accentuating the curve. Standing underneath the looming wave of rock, there's an uncanny sense of captured motion, a silent frozen moment from a time when geology, not water, danced in fluid form. Kalu Kalu in the Northern Territory. Scattered across a secluded valley in Australia's red centre are dozens of enormous rounded boulders, as if some giant toddler abandoned their marbles mid-play. This surreal boulder field is known as Kalu Kalu or the Devil's Marbles. These granite orbs, glowing red by day's end, perch precariously on one another or sit cracked in halves, seemingly defying gravity. To geologists, they are a textbook example of nature's boulder-making workshop, illustrating how time and weather can turn angular bedrock into nearly perfect spheres. The story of the Devil's Marbles began about 1.7 billion years ago, deep in Earth's crust. Back then, molten magma intruded into older rocks and slowly cooled to form a vast body of granite beneath a covering layer of sandstone. As the granite crystallized, it contracted slightly and cracked into large rectangular blocks, bounded by natural fractures or joints. For ages, the granite lay hidden, but ultimately, the overlying rocks were worn away by erosion, and the granite pluton was gradually exhumed, moving from the dark quiet of 10 kilometers depth to the harsh exposure of the surface. Once the granite reached the open air, weathering really began to work its magic. Water percolating down the remaining sandstone and soils attacked the granite along its network of joints. In the wet, humid climates of long ago, chemical reactions transformed the edges and corners of the granite blocks into softer clays. Corners and edges always weather faster. They're exposed on multiple sides, so gradually the blocks became rounded core stones enveloped in weathered rinds. Eventually, all the overburden was stripped away, releasing these rounded granite cores onto the surface. Wind and rain then continued the process, washing away the loose weathered material and further smoothing the boulders. The extreme climate of the outback also contributes to shaping the marbles. By day, the granite bakes in temperatures exceeding 40 degrees Celsius, expanding ever so slightly. At night, it cools and contracts. This daily pulse causes the rock's outer layers to weaken and peel off in sheets, a process called exfoliation. Over thousands of cycles, the boulders shed their weathered skins like onions, becoming rounder and rounder. Some split cleanly in half, perhaps from the stress of cooling or the prying of tree roots, leaving twin hemispherical domes that seem artfully placed by a giant hand. The rich red hue of the Devil's Marbles comes from the iron minerals in the granite, rusting at the surface, staining the rocks with a desert patina. Standing among these colossal orbs at sunrise is a mystical experience. The boulders balance improbably, some teetering on small points. They cast long blue shadows on the red earth, and as the sun climbs, the granite eggs blaze orange against the flawless sky. The Jenolan Caves in New South Wales. Deep in the Blue Mountains west of Sydney lies an underground wonderland that reveals the slow poetry of water in stone, the Janolan Caves. Hidden beneath a forested valley, this extensive karst cave system twists and turns for over 40 kilometres, with subterranean rivers, cathedral-like chambers, and a sparkling array of limestone formations. Stalactites hang from the ceilings like stone icicles. Stalagmites build from the floors, sometimes meeting to form columns. Delicate crystal shawls and flowstones drape the walls, their pure white calcite turning gold under flashlight beams. The atmosphere is cool and hushed, broken only by the occasional drip of water, the very same force that built these caves drop by drop. Jenolan is often hailed as the oldest known open cave system in the world, and indeed it is incredibly ancient. When you descend into its depths, you are effectively stepping into a realm that began forming hundreds of millions of years ago. Geologically, Janolan Caves owe their existence to a combination of very hard rock and very persistent water. The story begins around 430 million years ago, during the Silurian period, when the limestone here first formed as a coral reef or marine sediment in a shallow sea. That limestone, rich in marine fossils like ancient corals, brachiopods and other sea life, was later uplifted as part of the Great Dividing Range. Over eons, the once horizontal layers of limestone were tilted, fractured and exposed to the elements. Crucially, limestone is soluble in slightly acidic water. Fast forward to the past few million years, rainwater seeped down through cracks in the rock, enriched by carbon dioxide from the soil to form a weak carbonic acid. Following these cracks and joints, the water slowly dissolved the limestone, enlarging hairline fractures into tunnels and caverns. Jenolan's network of caves likely went through multiple phases of formation, some passages forming, then filling with sediment, then being re-excavated by new water flows. In fact, researchers using radiometric dating on cave clays have determined that parts of the Jenolan system are about 340 million years old, making it the oldest dated cave system so far. This astonishing age suggests that some cavities survived virtually intact since the late Carboniferous period, even as surface landscapes above were worn away. Over such a long span, the caves didn't remain static. Water continued to flow and reroute, carving new chambers and abandoning old ones. The subterranean Jenolan River still courses through some sections, continuing the work of dissolution in real time. Meanwhile, in the dry upper levels, formation growth takes centre stage. Every stalactite and stalagmite in Jenolan grew from mineral-rich water dripping or trickling in the dark. As each drop of water evaporated or lost carbon dioxide, it precipitated a tiny ring of calcite. Multiply that by millions of drops over tens of thousands of years, and grand formations result. Some of Jenolan's most famous features, the shimmering ribbon stalactites, the massive flowstone called minaret, or the eerily translucent shores in the Temple of Bund Cave, are the product of this slow decoration process. Geologically, they are evidence that the cave has remained stable for a very long time to allow such features to grow. Jenolan Caves thus represent a double marvel. They showcase one of the earliest chapters of cave development on Earth, and at the same time, they actively demonstrate ongoing geological processes. Walking through its chambers, one traverses an underworld that has outlasted mountains and oceans, where water and rock continue their ageless dance, sculpting ever so slowly the hidden contours of the Earth. The Pinnacles in Western Australia. Rising from the golden sands of the Nambung National Park, the Pinnacles Desert is an eerie expanse dotted with thousands of limestone pillars. These jagged spires range from knee-high stubs to 5-metre monoliths, casting long shadows across rippling dunes. Their shapes are fantastically varied, some are sharp and conical, others mushroom-like or stubby with rounded tops, creating an almost alien forest of rock amid an otherwise barren landscape. As the desert winds continually shift the sands, the pinnacles appear and disappear with time. Local lore even recalls a time when they were completely buried, only to be gradually re-exposed by the migrating dunes. Walking among these silent sentinels feels like stepping into a prehistoric sculpture garden, their surfaces etched by weathering and embedded with seashell fragments that hint at their origin. Belying their otherworldly appearance, the pinnacles are a product of very earthly processes, though geologists still debate the exact sequence of events that created them. Their story began roughly 500,000 years ago, when this area was a shallow coastal sea teeming with marine life. As the sea retreated about 25,000 years ago, it left behind masses of seashells that broke down into calcium-rich sand. These lime sands blew inland into dunes, eventually hardening into a rock layer known as the Tamala limestone. The pinnacles themselves formed within this limestone and were later exposed by erosion. Exactly how they formed is an ongoing mystery. Scientists have proposed several ingenious theories. One idea is that acidic rainwater dissolved the limestone into vertical hollows, solution pipes, and the remaining hardened material stands as the pillars we see. Another theory suggests the pillars might have begun as casts around the roots of ancient plants or trees that were cemented by minerals, then unveiled by wind erosion, long after the organic matter vanished. A more recent proposal even points to microorganisms, suggesting that microbes help cement the sand into these columns. In all scenarios, the key is that the limestone pillars proved more resistant than the surrounding sand, which was gradually eroded away by wind and water. Today, the Pinnacles endure as remnants of this complex interplay of marine deposition, groundwater cementation, and wind erosion, a process hundreds of thousands of years in the making. Standing amid them, one can't help but marvel at how time and chemistry conspired to turn an ancient seabed into a surreal desert gallery. The Glasshouse Mountains in Queensland. Jutting abruptly from Queensland's Sunshine Coast hinterland, the Glasshouse Mountains are a collection of craggy domes and spires that rise above the surrounding forests and fields. There are 13 main peaks, each with its own shape and character. These mountains have a striking isolated appearance. Steep-sided and nearly bare of vegetation on their upper slopes, they dominate the flat coastal plain like sentinels. The unusual name comes from history. When Captain James Cook sailed up Australia's east coast in 1770, he thought these peaks looked like the huge glass furnaces or glasshouses of his native Yorkshire, and thus dubbed them the Glasshouse Mountains. There is a familial similarity to the summits. All are made of the same greyish rock, and many exhibit sheer cliffs or vertical columnar structures on their flanks. The Glasshouse Mountains have long been sacred to the indigenous people, and today are popular with hikers and sightseers, offering panoramic views from their summits. But to geologists, these peaks are of special interest as windows into Australia's volcanic past. Unlike most mountains which form from uplifted crust or accumulated layers, the Glasshouse Mountains are actually the solidified cores of ancient volcanoes. Their story began about 25 million years ago, in the late Oligocene to early Miocene, when this part of Australia was geologically active. At that time, the Australian continent was drifting northward over a hotspot, a plume of magma rising from deep in the Earth's mantle. As the continental crust passed over this hotspot, volcanoes erupted through the overlying rocks, much like a blowtorch burning holes through a moving sheet. Dozens of small volcanoes would have dotted southeast Queensland's landscape. Then, around 26 to 27 million years ago, a different phase of activity occurred. Molten magma began pushing its way upward more slowly, intruding into the crust without completely breaking through as a lava flow or eruption. These intrusions formed dome-shaped plugs and laccoliths beneath the surface, essentially reservoirs of magma that cooled and crystallized underground. The Glasshouse Mountains are the solidified remains of these magma plugs. Over the millions of years that followed, all the surrounding material, the volcano's outer cones and the softer sedimentary rocks of the region, eroded away, leaving only the hard igneous cores behind. What we see now are those resistant cores, standing high as the landscape's softer parts have been worn down to a plane. The rock composing the peaks is mostly rhyolite and trachyte, hard volcanic rocks that cooled slowly enough to form columns and vertical jointing. For example, Mount Cuderin displays striking organ pipe columns, a clue that they cooled from a molten state in place. Geologically speaking, each mountain is like the exposed heart of an extinct volcano. As rainfall, wind, and time peeled away layer after layer of overlying rock, the bones of these volcanoes emerged. This process has produced the dramatic contrast we see today: lush subtropical lowlands punctuated by bare rocky mounts. The Glasshouse Mountains thus stand as time capsules of Australia's fiery origins, their bold shapes forever frozen reminders of volcanoes that raged here long before humans walked these lands. Flinders Ranges in South Australia. In the sunburnt heart of South Australia lies the Flinders Ranges, a landscape that forever changed the field of geology by revealing fossils so significant they led to the creation of an entirely new geological period, the Ediacaran. This long spine of weathered mountains, with its corrugated ridges and folded valleys, preserves an almost uninterrupted record of Earth's deep past. Here, the land itself seems ancient beyond measure. Craggy peaks of quartzite glowing red at sunset, layered slopes recording times of ice and times of tropical seas, and a ring-shaped natural amphitheatre called Wilpena Pound, lying like a crater of a lost volcano, though it is in fact a synclinal basin. The Flinders Ranges are not soaring like the Himalayas. Their highest summits barely reach 1,000 metres, but they once did. These ranges were once towering mountains, pushed skyward by tectonic collisions hundreds of millions of years ago. Since then, relentless weathering and erosion have stripped them down, layer by layer, leaving behind their hardened cores. Steep ridges of quartzite and slate that stand like the bones of a vanished giant. Yet in their subtle heights and twisted strata lies a geological epic, the rise and erosion of an ancient mountain range, and a treasury of fossils marking the dawn of animal life on Earth. The tale begins over 800 million years ago, when this part of Australia was a depression on Earth's surface known as the Adelaide Geosyncline or Adelaide Rift Complex. For hundreds of millions of years, that basin gathered sediment. Rivers and seas laid down sands, silts, and limey mud in layer after layer as life slowly evolved from single cells to complex forms. By around 600 to 540 million years ago, in the Ediacaran to early Cambrian period, those sediments had become thousands of meters thick. They recorded extraordinary events, among them 2 global ice ages that turned Earth into a snowball, and then warm interludes where an ancient reef grew here around 650 million years ago, one of the oldest reef systems known on Earth. But what truly sets the Flinders Ranges apart is what was found locked within these ancient layers: fossils of the Ediacara biota. Bizarre, soft-bodied sea creatures representing Earth's earliest complex life. The discovery didn't just fill a gap in the fossil record, it created an entirely new geological period, the Ediacaran, the first addition to the geologic timescale in over a century. This mountain range didn't just preserve Earth's deep biological history, it forever altered our understanding of when and how life first took hold. The Flinders Ranges hold pages of the planet's story that exist nowhere else, a near-continuous archive of the world waking up to life. Mountain building came next. Around 500 million years ago, as the supercontinent Gondwana was assembling, tectonic forces crumpled the sediments of the Adelaide Geosyncline like a carpet being shoved against a wall. This was the Dalamerian orogeny, which uplifted the Flinders Ranges as a chain of mountains. The layers folded and faulted. Wilpinnapound, for example, is a large syncline, a downfold, encircled by resistant quartzite ridges that were once sand on an ancient beach. At its centre, softer shales and limestones eroded away to create the Pound's broad flat basin. Over the unfathomable span of time since, the Flinders have been largely worn down. By 300 million years ago, the range was already reduced and gentler, yet the bones of the Earth remained. Hard quartzites, sandstones and dolomites that resisted erosion now form the high crests and steep walls of the gorges, while softer rocks became valleys and passes. In just the last 5 million years, very recent on this scale, there's evidence the land has risen slightly again, rejuvenating rivers to cut deep gorges and accentuate the relief of the ridges. Today, the Flinders Ranges undulate across the horizon in hues of umber, rust and purple. The air is dry and clear, carrying the scent of eucalyptus on the wind. In the craggy outcrops along Brachina Gorge, you can place your hand on ancient ripple marks of a long vanished sea, or on tillite rocks dropped by melting ice 700 million years old. Each layer in the cliff has a tale to tell, like chapters in an ancient chronicle. When dusk falls, the ranges ignite in fiery orange light, revealing every fold and crinkle of their form before subsiding into shadow against a bowl of stars. Few places on Earth offer such a tangible sense of deep time as the Flinders. These mountains, humble in height but epic in story, stand as Australia's geological memoir, a timeless, rugged and beautiful record of creation, destruction and persistence written in stone. Kings Canyon in the Northern Territory. In the heart of Australia's red centre, Kings Canyon yawns like a giant cleft in the earth, its sheer sandstone walls glowing red and orange in the desert sun. Part of Wataka National Park, this canyon's cliffs tower over 100 metres high, enclosing a hidden oasis of life in their depths. Up on the rim, the rock forms crazy shapes, notably the Lost City, a maze of beehive-like domes that crown a plateau, resembling the weathered ruins of an ancient city. Down below lies the Garden of Eden, a permanent waterhole fringed by palms and ferns, where water and shade offer refuge from the surrounding arid lands. The canyon's grandeur and its unexpected pockets of greenery have long made it a sacred place for the local indigenous people and a source of awe for visitors trekking the famous Ring Walk along its precipice. As the sunlight shifts, the walls change hue from golden to blood red to purple, revealing textures that record eons of geological history. Geologically, Kings Canyon is essentially a giant slice through time. Its story begins over 440 million years ago in the Paleozoic era, when sediments laid down in an ancient sea hardened into sandstone. The lower part of the canyon exposes the Carmichael Sandstone, a layer deposited about 440 million years ago, rich in fine grains from long ago beaches and seafloors. Above it sits the younger Morini sandstone, around 400 million years old, forming the high cliffs and escarpments. A thin band of purple shale between these layers marks an environmental shift in deep time, perhaps a period when the sea briefly withdrew, leaving mudflats that later solidified into stone. The canyon itself was carved much later, as natural forces exploited differences in rock hardness. Geologists estimate that by about 400 million years ago, water had begun cutting down through the softer upper sandstone. Over countless millennia, erosion by rain and flash floods along Kings Creek gnawed away at the plateau, widening fractures and carrying off debris. The harder Morini sandstone at the top resisted longer, eventually forming the vertical buttresses and overhangs, while the layers below were scoured out to create the gorge. Wind and temperature extremes also played a role, gradually shaping the Lost City domes on the canyon rim by rounding the edges of jointed rocks. Today, we see a cross-sectional view of this geological architecture. Horizontal bedding lines streak the cliff faces, and one can literally place a hand on the boundary between two ancient worlds of sandstone. Kings Canyon's very existence is a reminder that even in Australia's seemingly changeless outback, rivers and climate have been at work for ages, carving a masterpiece out of stone through persistence and time. Caragini National Park in Western Australia. In Western Australia's Pilbara region, Caragini National Park unfolds a dramatic landscape of deep chasms and iron-rich mountains, a place where the exposed rocks are among the oldest on the Australian continent. The story of Caragini's gorges begins over 2.5 billion years ago, when this area lay beneath an ancient ocean. Fine sediments saturated with iron and silica settled on the seafloor in alternating layers, building up what we now call banded iron formations. Over immense time, additional sediments piled on, the weight compressing the iron layers into tough, thin-bedded rock. Essentially rusted ancient seabeds turned to stone. Geological forces later gently uplifted this region into dry land. As the primordial ocean receded, erosion took over. Flowing water from rains and rivers exploited faults and joints in the rock, cutting even deeper. The result is Caragini's maze of spectacular gorges, carved over the last 20 million years as the climate oscillated and rivers entrenched into the rising plateau. Exploring Caragini, you descend into steep slots where walls of striped red rock tower above emerald pools. Each band in the gorge walls represents a chapter of Earth's early history. The rusty iron strata vividly painted in red, maroon and purple hues. The iron formations here are incredibly hard and ancient, yet water's ceaseless patience has sculpted them into smooth, fluted walls and cascading waterfalls. It is humbling to realise these rocks formed when life on Earth was microscopic. Now they form an epic landscape supporting spinifex grass, gum trees and wallabies. Caragini's gorges are cathedrals of deep time, offering a glimpse into the Archean world and showcasing the power of water to carve beauty from even the oldest stone. Mount Augustus in Western Australia. Rising out of Western Australia's remote Gascoyne region stands Mount Augustus. This colossal formation is often billed as the world's largest rock, an isolated Inselberg or island mountain that dwarfs even Uluru at over twice its size. Geologically, however, Mount Augustus is not a single solid monolith, but an asymmetrical anticline, essentially a vast fold of layered ancient sediments that has been bowed upward into a dome. The story of Mount Augustus's creation spans almost an incomprehensible timeframe. Around 1.6 billion years ago, an ancient river system coursed over this area, depositing huge quantities of sand and gravel across a granite bedrock. These sediments gradually compacted and cemented into hard sandstone and conglomerate layers. In the eons that followed, shallow seas submerged this region. The riverine sandstone became buried beneath younger marine sediments laid down between 1.6 and 1.07 billion years ago. All this weight caused the lower layers to sink and lithify further, entombing Mount Augustus's precursor under countless tons of additional rock. Later, monumental forces within the Earth began to thrust these strata up. About 900 million years ago, movements along deep faults in the Earth's crust compressed the region from the northeast. This intense pressure buckled the sedimentary layers into a massive arching fold, uplifting the sandstone and conglomerate into the broad dome we now recognise as Mount Augustus. Over subsequent ages, erosion went to work on the elevated structure. Wind and water gradually stripped away the softer overlying marine rocks, as well as parts of the sandstone at the flanks of the fold, exposing the resistant core of ancient sandstone and conglomerate. What remained isolated above the surrounding terrain was the mighty bulk of Mount Augustus, while the eroded materials now form lower hills and plains around it. Today, Mount Augustus towers about 860 metres or 2,820 feet above the flat plains, reaching a peak elevation of 1,105 metres above sea level. The mountain's base stretches over 8 kilometres in length, a solitary ridge so large it can be seen from the air more than 160 kilometres away. Its rust-hued flanks glow orange-red under the outback sun, cut through with gullies and gorges that channel the rare rainfall the area receives. Unlike the mostly barren Uluru, Mount Augustus's slopes even sustain scattered vegetation. Hardy wattles and shrubs cling to its crevices, nourished by groundwater that trickles down the ancient rock. Standing at its foot, one truly feels the presence of deep time. Here you can literally touch sandstone formed from river sediments older than multicellular life on Earth. Geologists estimate the rocks of Mount Augustus formed about 1.65 billion years ago, making this enduring giant one of the oldest exposed rock formations in the world. It carries in its layers the memory of vanished rivers and seas, and the upheavals of primordial continents. The Wolfe Creek crater in Western Australia. In a remote corner of the East Kimberley, the Earth opens into a near-perfect circle, Wolfe Creek crater. This impressive crater is about 875 metres across and 60 metres deep, with a raised rim that rises some 20 metres above the surrounding plain. For a long time, scientists believed the crater to be around 300,000 years old, but recent studies showed it formed much more recently, roughly 120,000 years ago, placing the impact in a late Pleistocene epoch. The site remained unknown to Europeans until 1947, when it was spotted during an aerial survey of the desert. Wolfe Creek crater is today recognised as the second largest meteorite crater in the world, from which meteorite fragments have been recovered, and its remote location and arid climate have left it remarkably well preserved. The extraterrestrial culprit responsible for the Wolfe Creek crater was a massive iron meteorite, estimated at about 15 metres in diameter and weighing over 50,000 tonnes. It slammed into the ground at roughly 15 kilometres per second or 45,000 kilometres per hour. The impact was cataclysmic. In the blink of an eye, this meteorite exploded on contact, releasing energy equivalent to multiple atomic bombs. The shockwave punched out a circular hole nearly a kilometre wide, heaving up an encircling rim of jumbled debris. The intense heat and pressure of the collision liquefied rock and metal at the site, even melting the desert sand into glassy beads. In that violent instant, tons of earth and meteorite material were vaporized or hurled skyward. What remained was a deep bowl-shaped crater, its interior strewn with fragments of the meteorite itself. Many of those remnants have since oxidized into rusty iron shale balls, some weighing up to hundreds of kilograms, now found scattered around the site. Today, Wolfe Creek crater appears almost otherworldly in its desolate setting. Peering down from the rim, one sees a flat, hard-pan floor inside the crater, where hardy shrubs and saltbush now grow. The crater's floor lies about 25 metres lower than the land outside, so it acts as a natural catchment for the scarce rainfall in this desert region. After rare rains, water pools temporarily on the crater floor and then seeps into the ground, creating a slightly greener haven in the arid landscape. In fact, the centre of the crater contains gypsum-rich soils that hold moisture longer, evidenced by a cluster of surprisingly large white-trunked eucalyptus trees flourishing where few others can. Around the inner walls, one can clearly see the classic impact crater features, the steep sloping sides and the raised rubble rim formed by ejecta. Because Wolfe Creek has suffered little erosion, it remains a textbook example of a young meteorite crater, a natural laboratory showing how such impact structures look shortly after formation. The Great Barrier Reef in Queensland. Off the northeast coast of Australia lies a geological wonder that is very much alive. The Great Barrier Reef, a sprawling mosaic of vibrant corals and turquoise lagoons visible even from space. It is the world's largest coral reef system, comprising some 2,900 individual reefs and 900 sandy islands that arc along 2,300 kilometres of the Coral Sea. Flying over it, you see a maze of reef patches and atolls in every shape, crescent reefs curling around calm lagoons, ribbon-like reefs stretching along the continental shelf, and patch reefs dotting the shallow sea. Beneath the water, this wonderland bursts with marine life. Rainbow-coloured corals build ornate calcium carbonate structures, while darting reef fish, sea turtles and sharks weave through coral canyons. In fact, the Great Barrier Reef is the planet's largest single structure made by living organisms. billions of tiny coral polyps whose limestone skeletons have merged over time into a colossal natural edifice. It's no surprise the reef is counted among the natural wonders of the world. But it is also a geological edifice with a dynamic history tied to changing seas. Though teeming with life, the Great Barrier Reef is fundamentally a geological formation of limestone and coral sand, one that has grown and shrunk in rhythm with the ice ages. The reef's roots go back less than 1 million years, surprisingly young in geological terms. Under the seafloor, the foundation consists of older Pleistocene reef platforms and even remnants of long-dead volcanoes that form the hills and islands of the Queensland coast. As Australia inched northward into tropical latitudes about 25 million years ago, conditions became favourable for coral growth, but river sediments and fluctuating sea levels often stifled early reef development. The modern Great Barrier Reef began to take shape after the last ice age. Around 20,000 years ago, sea level was dramatically lower, about 120 metres below today's level, and much of the continental shelf was exposed land. With the end of the ice age, sea levels rose and warm waters flooded the shelf, allowing corals to colonise new ground. According to the Great Barrier Reef Marine Park Authority, the reef's oldest section started growing roughly 600,000 years ago, but the reef as we know it is far newer. In fact, the current living reef structure began only about 9,000 years ago, after the last glacial melt drowned the previous coastal lowlands. Corals grew upward frantically to keep pace with the rising seas, building on the limestone foundations of older reefs. By around 6,000 to 8,000 years ago, sea level stabilised near its present position, and the reefs could expand laterally into their present-day configuration. To this day, the reef continues to grow. Individual corals lay down a few millimetres of new limestone each year, and reefs can grow vertically up to 25 centimetres per year in ideal conditions, though growth slows as they near sea level since corals cannot survive long out of water. Essentially, the Great Barrier Reef is a gigantic natural construction project in progress for millennia. Its existence reflects a delicate balance. The corals require warm, clear, sunlit waters, so the reef flourished during high seas and warm interglacial periods, and paused or died off when seas fell or waters cooled. The result is a layered geologic record beneath the living reef. Drill cores have found alternating bands of ancient reef limestone and old soil layers, evidence of reefs growing and then dying as sea levels fluctuated. Today's reef is merely the latest incarnation in a series of reefs, but it is by far the largest and still expanding at the edges. It stands as a living geological wonder, at once a thriving ecosystem and a massive structure of stone built by tiny polyps sensitive to the planet's heartbeat of ice ages and thaws. Pine Mountain in Victoria. Tucked away in the remote highlands of northeast Victoria is one of Australia's least known but most monumental landforms. Towering above the surrounding forested hills, Pine Mountain is Australia's largest monolith, a massive singular mountain of granite that quietly dominates the skyline. Rising over 1,000 metres above sea level and stretching more than 1.5 times the length of Uluru, Pine Mountain is an inselberg of staggering proportions. But unlike Uluru's smooth red sandstone, Pine Mountain is built from tough crystalline granite, rock that formed not at the surface but deep within the Earth's crust over 400 million years ago. The story of Pine Mountain begins during the Devonian period, a time of major tectonic change in what is now Victoria. After intense mountain building during the Tabaraba and orogeny, the thickened crust began to relax and heat from below. Pine Mountain is part of the Corryong batholith, an S-type granite formed from melted sedimentary rock in place during the late Devonian. Deep within this crust, ancient sedimentary rocks partially melted, producing a slow-rising body of granitic magma. Over time, that magma cooled and crystallized into coarse-grained granite, rich in quartz, feldspar and mica. This massive pluton remained buried for hundreds of millions of years, until erosion stripped away the overlying rock, revealing the giant granite core we now see as Pine Mountain. Because granite is highly resistant to weathering compared to most sedimentary rocks, it withstood the elements even as the surrounding land was worn down. What remains today is a classic inselberg, an isolated mountain rising abruptly from a lower surrounding plain, left behind as the rest of the landscape eroded away. Geologically, Pine Mountain is not a smooth dome, but a fractured and complex granite mass. Exfoliation joints, formed as pressure was released during erosion, have caused the granite to peel off in curved sheets, giving the mountain its rugged appearance. Weathering and rainwater have carved narrow gullies, and over time, frost and chemical erosion have pried apart the rock into large boulder clusters that litter the slopes. Some of these boulders, weighing several tons, now sit perched in precarious positions, natural sculptures shaped by deep time. But Pine Mountain is not just a scenic wonder or a massive block of granite, it's a tangible remnant of Devonian tectonics, a monument to the inner workings of Earth's crust, and a masterclass in slow-motion erosion. It has stood for hundreds of millions of years as a witness to the rise and fall of continents, the shifting of climates, and the relentless grinding of the Earth's surface. Quietly, it towers above the valleys of northeast Victoria, not as a tourist icon, but as a geological epic written in stone. The Undara Lava Tubes in Queensland. Beneath the rustling grasses of North Queensland savanna lies a vast and ancient secret, a subterranean landscape carved not by water or ice, but by fire. The Undara Lava Tubes, hidden beneath the dry terrain of Undara Volcanic National Park, are among the longest and best preserved lava tubes on Earth. Their creation began roughly 190,000 years ago, during the late Pleistocene, when a volcano in the McBride Volcanic Province erupted with extraordinary force. The eruption was not short-lived. It may have continued for weeks or even months, pouring out an estimated 23 billion cubic meters of lava, enough to blanket a region the size of Sydney Harbour many times over. This lava, basaltic in composition and extremely fluid, fanned out over the landscape in vast rivers of molten rock. Some flows extended up to 160 kilometers from the eruption site, making them among the longest known lava flows on the planet. As the outer surfaces of these lava rivers met the cooler air in ground, they began to cool and solidify, forming thick crusts. Beneath these rigid surfaces, the lava kept moving, hot, fast, and insulated. Eventually, as the eruption waned and the source of lava diminished, the molten rock drained away, leaving behind hollow cylindrical tunnels carved by fire. These became the Undara Lava Tubes, monumental conduits through which the Earth once exhaled its molten breath. What makes Andara extraordinary is not just its size, but its state of preservation. In most volcanic regions, lava tubes collapse over time. Their ceilings cave in, their interiors lost to erosion or sediment. But the arid climate of inland Queensland and the protective basalt caprock helped shield many of these tubes from weathering. Some of these tunnels stretch for more than a kilometre without interruption, with widths reaching up to 22 metres and heights towering to 10 metres in places. Over 70 distinct tubes and caves have been discovered in the park, forming a complex underground network that has remained largely unchanged since the Ice Age. Above ground, sections of the tube roof have collapsed, forming natural entrances that now let in shafts of light, allowing trees, vines, and ferns to reclaim small pockets of the dark. These openings, known as collapsed-lines, create dramatic sinkholes where wildlife flourishes. Inside, the tubes are adorned with frozen ripples and ropes of basalt, silent evidence of the lava's once fluid movement. In the still air, colonies of bats roost on the walls, and in some chambers, tree roots hang down like chandeliers. Walking through these cavernous passages is like stepping into a preserved moment of Earth's volcanic past. But Andara is more than a geological oddity, it is part of a much larger volcanic province, the McBride Basalt Field, which covers over 160 volcanoes and lava fields spanning nearly 5,500 square kilometres. This broader volcanic region has been active on and off for the last 8 million years, but the Andara eruption remains one of its most significant events. The Undara Lava Tubes are not just a natural spectacle, they are a geological time capsule, preserving the motion and heat of a world long gone. The 12 Apostles in Victoria. Along the stormy coast of Victoria, where the Southern Ocean's breakers relentlessly pound limestone cliffs, stand the 12 Apostles. Majestic sea stacks that rise like rugged towers from the surf. They march in staggered formation offshore, remnants of a coastline that has been gnawed away by the waves. Though named the 12 Apostles, only 7 stacks remain above the waves today, the others claimed by the very ocean that created them. The story of the 12 Apostles is relatively youthful in geological terms. Their tale begins in the mid-Miocene, around 15 to 20 million years ago, when this part of Australia was submerged beneath a shallow sea. In those seas, countless marine organisms thrived and died, their calcareous skeletons accumulating on the seafloor. Over time, those carbonate sediments lithified into the Port Campbell limestone, a soft, yellowish sedimentary rock riddled with fossils and held together by calcite cement. For millions of years, the limestone layers built up, only to be later uplifted with the continent and exposed as coastal cliffs when sea levels fluctuated. By the end of the Miocene, global cooling had begun to influence sea levels, and over the following millions of years, glacial cycles caused the ocean to rise and fall dramatically. These fluctuations set the stage for the Southern Ocean to begin its ongoing work, carving away the limestone cliffs of Victoria during high stands and exposing them to wind and weathering during low stands. The relentless waves first attacked weaknesses in the cliffs, perhaps a zone of fractured rock or a softer band in the limestone. Sea caves were gouged out at the cliff base as each wave pried out fragments and acid in the seawater slowly dissolved the calcium carbonate. With time, caves on opposite sides of the headland met in the middle, forming arches that bridged the foaming water. The process continued, day and night, the roaring surf chewing away at the foundations of these arches. Eventually gravity won, an arch would collapse, and the isolated pillar of harder rock between the collapse and the receding cliff was left standing as a new sea stack. Thus were the 12 apostles born from cliffs that themselves are steadily retreating. Each stack stands roughly 45 to 50 metres high, a temporary monument destined to be worn away. Indeed, in 2005, one 50-metre apostle collapsed dramatically into the sea, reminding us that this coastline lives in geologic real-time, changing faster than our eyes often perceive. Seeing the apostles from the clifftop, one can appreciate their constant battle with the elements. Wind whistles over the Southern Ocean, whipping up whitecaps that crash at the stack's bases, eroding them grain by grain. The limestone's pale surface is pitted and sculpted, and each apostle is fringed with fallen boulders at its foot, where chunks have sheared off in recent years. Yet for all their vulnerability, the stacks have a certain stoic grandeur. In the soft light of dawn or dusk, they stand like sentinels in the mist, the endless roar of the ocean around them. Every apostle contains within it millions of ancient marine fossils, a hardened fragment of an oceanic past now upstanding in the present. Lake Hillier in Western Australia. Tucked away on remote Middle Island, off Western Australia's southern coast, lies Lake Hillier, a bubblegum pink lake so vivid it almost seems otherworldly. This small salt lake, about 600 metres long and 250 metres wide, is separated from the Southern Ocean by only a thin strip of white sand dunes and vegetation, creating a striking colour contrast between pink and blue. The surrounding shoreline is often encrusted with white salt, further accentuating the lake's rosy hue against the emerald green island foliage. Seen from above, Lake Hillier appears as a solid patch of cotton candy pink, encircled by paperbark and eucalyptus woodland, and a turquoise ocean beyond, a living palette of colours unlike anywhere else in the world. Unlike most colourful lakes, Lake Hillier's rosy hue is permanent. If you bottle a sample of the water, it stays pink. The secret lies in the lake's unique chemistry and biology. Its waters are extremely saline, and they host communities of halophilic or salt-loving microorganisms. One such alga thrives in the briny environment and produces large amounts of beta-carotene, a red-orange pigment also found in carrots. Additionally, halobacteria in the water contribute reddish pigments like bacteria ruberin. Together, these pigments tint the lake a vivid pink year-round. The high salinity also leads to salt crusts forming at the lake's edge, where halobacteria often live, giving the shoreline a rim of white and faint orange-red. Despite its unusual colour and chemistry, the lake's water is thought to be harmless to humans, though its isolation means few get a chance to wade into its pink brine in person. Lake Hillier was first documented by European explorers in 1802, when British navigator Matthew Flinders came upon this curious rose-coloured lagoon. Flinders recorded in his journal how the lake was of a rose colour, and so saturated with salt that plentiful crystals had formed along the shore. In fact, for a short time in the late 19th century, the lake was mined for salt, though operations were soon abandoned. Today, Lake Hillier is part of a protected nature reserve and remains one of Australia's most eye-catching natural curiosities. Its remote location means it's not easily accessible. Visitors typically must charter a scenic flight or boat tour from Esperance to glimpse its neon-pink waters from the air or a distant shoreline. This seclusion has helped preserve the lake's pristine condition. For those lucky enough to see it, Lake Hillier offers an unforgettable spectacle. A bright pink jewel nestled in emerald green island greenery, forever lapping against a beach of salt and sand. The Bunda Cliffs in South Australia. At the far edge of the vast Nullarbor Plain, the Australian continent ends abruptly in a jaw-dropping wall of sea cliffs known as the Bunda Cliffs. For over 200 kilometres, the land plunges suddenly and dramatically into the Great Australian Bight, forming one of the longest uninterrupted lines of sea cliffs in the world. These sheer bluffs, towering 60 to 120 metres high, create the impression of standing at the edge of the world. On one side, the table-flat expanse of the treeless Nullarbor, on the other, an endless cobalt blue ocean pounding the cliff base far below. Travellers driving the remote air highway can stop at windy lookouts where the cliffs extend to the horizon in a gentle curve, vanishing into a haze of sea spray. With waves crashing against monumental chalk white walls and wheeling seabirds far beneath your feet, the Bunda Cliffs offer a humbling vista of land meeting sea in its rawest form. Geologically, the Bunda Cliffs are carved from an ancient limestone seabed that was uplifted tens of millions of years ago. The story of their formation traces back to the Eocene epoch, when Australia split away from Antarctica around 50 million years ago, and the underlying Euclid Basin limestone was raised above sea level. The Nullarbor coast, once submerged, became exposed to relentless Southern Ocean swells. Over eons, powerful surf and saltwater aggressively eroded the soft limestone, undercutting and gnawing into the cliff's base. Bit by bit, the coastline receded northward, leaving behind a continuous towering escarpment, essentially the rim of Australia's limestone slab sliced clean by the sea. In the exposed cliff faces, you can read layers of geologic history. Along the lower cliff, a band of bright white Wilson Bluff limestone is visible, a chalky rock formed from an ancient seabed when Australia began drifting from Antarctica. Above it lie striations of whitish, grey and honey-brown limestone, some containing marine fossils like mollusks. The very top of the cliffs is capped by a hardened layer of wind-blown sandstone and soil deposited in later epochs. This stacked palette of colours and textures, white base, golden brown top, is clearly visible when sunlight strikes the cliffs, each layer recording a chapter of lost geologic time. Experiencing the Bunda Cliffs is a visceral encounter with geologic grandeur. Standing on a gusty clifftop lookout, one can gaze along the line of cliffs as it bends away for dozens of kilometres, the Great Australian Bight churning at their feet. Far below, aquamarine waves batter the cliff base with a distant thunder, throwing up mist that clings to the escarpment. In several places, huge chunks of cliff have collapsed in the past, creating coves and beaches accessible only from the water. The sense of isolation is profound. This coastal stretch is sparsely inhabited and utterly exposed to the elements. Whether viewed from the deck of a ship or from the window of a light plane, the sight of the Nullabor's abrupt 90-metre plunge into the sea is unforgettable. The Blue Mountains and Three Sisters in New South Wales. Just 50 kilometres west of downtown Sydney, the landscape rises into the Blue Mountains, a vast highland plateau of rugged sandstone that has been sculpted by nature into maze-like gorges and pinnacles. Geologically, the Blue Mountains are a dissected sandstone plateau, essentially a huge block of ancient sedimentary rock that has been uplifted and then carved by erosion into a complex of ridges, cliffs and valleys. The story of its rocks begins over 250 million years ago, in the Permian and Triassic periods, when the region was a low-lying basin of rivers, floodplains and swamps. Over long spans of time, those rivers dumped vast quantities of sand and silt, which were buried and compressed into layers of sandstone and shale, with swamp vegetation forming coal seams in places. Later, tectonic forces gently uplifted the entire sandstone basin, raising it into a broad plateau. From that point onward, water became the master sculptor. Millions of years of rainfall and flowing rivers ate away at any weaknesses in the rock. The plateau was gradually dissected into a series of knife-edged ridges, separated by steep-walled gorges, some plunging up to 760 metres deep into the earth. Sheer cliffs now flank the valleys, and dramatic rock formations crown many of the ridge tops. It's hard to imagine that this dramatic topography was once a relatively flat expanse of sediment, a transformation that speaks to the power of natural erosion on Australia's Triassic sandstone heart. The most iconic rock formation in the Blue Mountains is undoubtedly the Three Sisters, three slender sandstone spires that jut out from the cliff at Echo Point near the town of Katoomba. Rising roughly 900 metres above sea level, these pillar-like peaks are lined up along the escarpment's edge, almost like three sentinels overlooking the Jameson Valley. Geologically, the Three Sisters were once part of the main sandstone cliff itself. They formed as wind and water erosion worked their way into softer vertical joints or cracks in the sandstone, gradually isolating chunks of the cliff which became pinnacles over time. Today, the spires stand apart from the cliff by only a few metres. A narrow rock bridge or buttress connects to the first sister, and they continue to be slowly worn down by the elements each year. The rock is horizontally layered, and you can see lighter orange-yellow fresh rock where recent erosion or rockfalls have occurred. In the golden light of late afternoon or sunset, the Three Sisters glow with shades of amber and ochre against the green valley below. A spectacular sight, often photographed by visitors. These places prove just how weird and wonderful Earth's surface can be. They're not just beautiful, they're geological time capsules. Each one tells a story of ancient seas, shifting plates, relentless erosion, and strange chemistry. Stories written in stone, salt, and sediment over millions of years. I hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.